Welcome back. If you're running any kind of serious network, you know the feeling. That fine line between a minor glitch and a full-blown catastrophe. And it usually comes down to knowing the really specific, sometimes obscure details of how your gear acts under pressure. So today, we are doing a masterclass in advanced network troubleshooting. We're looking at security failure analysis, specifically using the FCSS NSE 7.6 framework, which is all about FortiOS 7.6.2 behavior as our guide. But, forget the exam itself. This is about giving you the practical know-how to solve these complex problems in minutes, not hours.
That's it, exactly. Our whole mission here is to just cut through that complexity and give you the actionable stuff, the core insight. We're looking at the real root causes of failure. Why do routing protocols just refuse to talk to each other? What really happens when your firewall is about to run out of memory? We're giving you the mental shortcuts to be that go-to person in the data center.
Okay, so much to get into here, I think. I think we need to unpack this. Let's start right where the headache usually begins for everyone. Routing instability. Specifically, adjacency failures. Let's start with OSPF, a classic. So you're troubleshooting, and your OSPF routers, they just will not form an adjacency. They're stuck. And they're stuck in that X-start state, it's incredibly common to see for anyone who might be a bit rusty. What is it about that specific state, X-start, that's so important in the OSPF handshake?
Well, the X-start state is basically the negotiation phase. It's the moment the routers are trying to agree on how they're going to exchange their databases. So if they get stuck there, it means they couldn't even agree on the basic rules of the conversation. They haven't even started talking about the actual network map yet. And our sources point to two really critical mismatches that will lock routers in X-start forever. The first one, and honestly probably the one people overlook the most, is a maximum transmission unit mismatch, an MTU mismatch.
The MTU size, okay.
Right. So if router A sends out its first packet, the database description packet, and router B's interface sees it as too big for its configured MTU, it just drops it silently.
And the process just stalls right there. It's like one person is shouting and the other is whispering, and they can't even agree on a volume.
That's a great way to put it. They can't calibrate.
So what's the second critical mismatch then?
The second one is the network type setting. OSPF needs to know if it's on a broadcast network or a point-to-point link.
Yeah.
If you have one router configured for broadcast and the other for point-to-point, they have totally different ideas about who should be the master and who's the slave in that exchange.
So they can't even decide who talks first.
Exactly. And the adjacency just stalls out indefinitely. They have to agree on the size of the conversation and the hierarchy before anything else happens.
That makes perfect sense. Okay, let's switch gears a bit. Let's talk about the backbone of the internet, BGP. So you have a successful peering. You can see the route in your BGP database. It's right there, but it's not in the mean routing table, the RAB. It's not being used to forward traffic. So why would BGP learn a route and then just decide it's completely useless?
It really gets to a core difference in how these protocols work. BGP is, well, it's really just a collector of advertisements. It records what its neighbors claim they can reach.
Right.
But for that route to get installed in the local RAB, the device has to check if it's actually a valid, usable path for forwarding traffic. And the number one reason this fails, the core insight here, is that the next hop IP address for that BGP route is unreachable.
Unreachable.
Or unresolvable in the local routing table.
So wait, the big important BGP route is totally dependent on some other smaller internal protocol.
Precisely. BGP might tell you how to get to a destination 10,000 miles away, but it's relying on your local OSPF or even just a static route to figure out how to take the very first step. If you can't resolve that first hop to the BGP next hop router, the entire route is invalid. It never gets into the RIB. It's useless.
That's a scary dependency. The stability of your entire internet connection could hinge on one tiny little local route being perfect.
It's why routing validation is so critical.
Okay, so let's say we get our routing sorted out, but the network is still, tearing itself apart. We have to talk about preventing catastrophe. Let's shift to high availability clusters. The absolute nightmare scenario here is split brain.
Oh yeah. Split brain is every network admin's worst fear in an HA setup. It's what happens when the two units in the cluster lose contact with each other. And when that happens, they both decide, okay, I must be the only one left.
So they both become the primary.
They both try to be the primary. They both start handling traffic, writing configs. It's just chaos. Total operational inconsistency. The cause is always the same thing, a failure of that communication heartbeat. And the sources point to two main ways this happens. First is the obvious one. The physical heartbeat links get unplugged or the cable goes bad.
Right.
The second one, and this can be a bit trickier to spot in a panic is that the switch connecting those heartbeat interfaces has failed completely.
Ah, so if the switch dies, from the firewall's perspective, it looks exactly like someone just cut the cables.
Exactly right. The heartbeat traffic, which is the lifeblood of that cluster, just stops. And because neither device can confirm its partner's status, the logic forces them both to assume the worst and take over.
You lose the communication, you lose the cluster.
Simple as that.
All right, let's go from an external catastrophe to an internal one. Memory. FortiGate firewalls have this state called conserve mode. It kicks in automatically when memory usage gets really high. It sounds like an emergency brake. What is the device actually doing when it slams on the brakes to avoid a crash?
Conserve mode is the system's very aggressive attempt to prevent a hard crash, to keep itself online. When memory usage crosses a certain threshold, usually around 85%, the OS has to make a sacrifice. It has to free up memory and fast. And the specific action it takes is to stop doing its most memory-intensive security jobs.
Which are what?
It immediately halts things like antivirus scanning and the intrusion prevention system, the IPS, all that deep packet inspection. It basically turns off the security modules that eat the most RAM.
Wow, that's a huge trade-off. You're suddenly less secure, but you're guaranteeing stability.
Exactly. It's a fail-open approach. By shedding that inspection load, it frees up critical resources, it keeps the packet engine stable, and it allows basic traffic to keep flowing. It prevents a total network outage.
Okay, that's the system stability side. But now we get to the part that I find, well, I think really interesting, and that's the trust and tunneling aspect. Let's look at one of the most common help desk tickets out there, certificate warnings. Your admin turns on full SSL inspection, and suddenly all the users are getting browser warnings on every HTTPS site. Why is the browser screaming at them when the security feature is technically working?
This is such a classic. It's a trust gap, not a problem with the website itself. When you enable full SSL inspection, the FortiGate has to intercept that encrypted traffic. It has to act as a man in the middle.
A good man in the middle, hopefully.
A transparent good one, yes. So it decrypts the traffic, inspects it, and then it has to re-encrypt it to send it to the client. And to do that, it resigns the traffic with its own certificate, its own CA.
Ah, and there's the problem.
There's the problem. The specific cause of that browser warning is that the user's computer doesn't trust the CA certificate being used by the FortiGate. The browser sees a certificate from some internal device it's never heard of, not a public one like DigiCert, and it immediately throws up that warning.
So the solution is just to make the clients trust the firewall certificate.
That's all it is. You push the FortiGate CA certificate out to your client's trusted certificate store, and the warnings disappear.
It's just the client saying, hey, I don't know who this middleman is.
Exactly.
Let's pivot from that to IPsec VPNs, another common headache. Phase 1 is up, the peers have authenticated, everything looks good, but Phase 2 keeps failing, and no traffic is actually passing through the tunnel. What are the two absolute must-match requirements for Phase 2 to succeed?
Phase 2 is all about the data itself. It's defining the protective bubble for the traffic. And if it fails, it means the peers couldn't agree on either what to protect or how to protect it. The first mandatory match is something called the quick mode selectors.
Quick mode selectors.
These are just the source and destination subnets. They define what traffic is allowed in the tunnel. If one site says protect the 192.168.1.024 network, and the other site says only protect the single IP 192.168.1.0, the negotiation fails right there. The package contents have to match perfectly.
Okay, that makes sense. What's the second one?
The second is the proposal settings. This is the how. It's the encryption algorithms like AES 256 and the authentication algorithms like SHA 512. And these have to be absolutely identical on both ends. Unlike Phase 1, there's basically no negotiation flexibility in Phase 2.
Yeah.
It has to be a perfect mirror or the tunnel just won't come up.
Any tiny difference is an automatic deal breaker.
It is.
Okay, let's get into a more sophisticated security check, the reverse path check fail, or RPF. This is a very targeted reason for dropping a packet. What technical condition exactly causes an RPF check failure?
RPF is really an anti-spoofing tool. It's all about enforcing routing symmetry. So when a packet arrives on an interface, the firewall does a quick check, and it drops the packet if it arrived on an interface that the routing table would not use to send a reply back to that source IP.
Hold on, that sounds a little counterintuitive. Why does the outgoing path matter for an incoming packet?
Because the firewall is asking itself a really fundamental question. It's asking, if I needed to reply to this source IP, which interface would I use? And if its routing table says I would use interface B, but the packet just showed up on interface A, it raises a red flag.
It assumes something is wrong.
It assumes one of two things is happening. Either the packet source address is maliciously spoofed, or there's a serious asymmetric routing problem in your network. Both are bad. So it drops the packet as a defense.
That's a brilliant security layer. It's checking the packet's passport, basically.
You could say that, yeah.
All right, moving on to user identity. Fortinet single sign-on, FSSO. Admins can choose between agent-based or agentless polling to get user info from domain controllers. So why wouldn't I just always use the easier agentless method? Under what condition am I forced to install an agent?
Right. Agentless is definitely cleaner. It just uses standard WMI queries from the FortiGate directly to the domain controller.
Yeah.
No extra software to install. But those queries, they can be pretty resource intensive if you have a lot of users.
Yeah.
And the sources confirm the one condition where you have to switch to agent-based mode is when your domain controllers are overloaded, when they just can't handle the constant polling from the firewall anymore.
So the DC is just getting hammered with requests and it's slowing down.
Exactly. It's struggling to keep up. So you install the agent on the DC itself to act as a relief worker. The agent handles the job of watching logon events locally and just sends the updates, which is much less strain on the DC's core functions. It offloads that work.
That makes sense. Let's talk automation now. Security fabric. The goal is a self-healing network. When you build an automation stitch, what are the two bare minimum, absolutely required components?
Automation stitches are the building blocks of any dynamic defense. It's just cause and effect programming. And you only need two things to make one work. First, you need a trigger. That's the event. A high-severity log, maybe, or just a scheduled time.
The if-this part.
The if-this, exactly.
Okay.
And second, you need an action. That's the response. The then-that.
Like sending an email or blocking an IP.
Right. Send an email, block an IP, run a script. You can add all sorts of other intelligence with FortiAnalyzer and things, but at its absolute core, an automation stitch is just a trigger and an action.
Simple logic. If X happens, do Y.
That's all it is.
Okay, finally. Let's hit a really common frustration that's tied to external services. FortiGuard. Your internet connection gets a little flaky, the FortiGuard rating servers are unreachable, and suddenly nobody can get to any websites. What's the one setting that lets traffic keep flowing when that external service fails?
This is a huge service continuity issue. If your firewall policy is set to be very strict and block any site it can't classify, then losing connection to FortiGuard means it can't classify anything.
So it defaults to blocking everything.
And you have a self-inflicted outage. To prevent that, the admin just needs to allow websites when a rating error occurs setting. It's basically telling the device, hey, if you can't get a rating, just let it through for now. It trades a temporary loss of web filtering for guaranteed uptime.
Which is often the more important thing in that moment.
For most businesses, yes. And we'll leave you with a final thought, building on that last point about service continuity. Considering that solution of allowing traffic when a FortiGuard rating fails, how should a network administrator balance that need for uninterrupted service against the risk, however brief, of letting unclassified or maybe even malicious traffic through? That fundamental trade-off between a seamless user experience and absolute security is something every organization has to keep thinking about.